Thank you, Andrew. So thank you, Philip, for joining us today. Thank you, everyone else who's joining us as well. So Philipp Hennig is he's going to be giving our talk this afternoon. And Philip is a professor of methods of machine learning at the University of Tübingen. Philip started his PhD as a physicist, I believe, as an undergrad at Heidelberg, before later then transitioning from physics into machine learning through a PhD at the University of Cambridge. His PhD was supervised by David McKay around about 2010. I'd like to say you finished your PhD. Excellent.
Yes.
Good.
Yeah.
So Philip's research, I would say, is very much on the sort of probabilistic side of machine learning. A lot of work around Gaussian processes, Bayesian optimization, probabilistic approaches for solving ordinary differential equations. And in the past few years, that's maybe 5 years or so, I know Philip has been quite keen on this area of probabilistic numerics, which is quite a new and developing area. And it's also the theme of today's talk. So I'll let Philip take it away and tell us all about probabilistic numerics.
Thank you very much. Let me just first share my screen and make sure that it actually works. Okay, now I've lost the list of participants and instead I see a list of faces. It's also good. Thank you very much to Chris and Andrew for the nice introduction, for having me. Thanks to CUP and Lloyd's Register and the Alan Turing Institute for running this seminar series. I'm very happy to be here and to be invited. I should start with well, first of all, actually an apology and maybe an invitation to you. So I've been looking at the list of participants coming in and I've seen a few faces that I know. And I've been wondering whether the title of my talk is a little bit too bold and too broad. So let me first check and see also if you are able to press your raise hand button. Who of you knows the term probabilistic numerics? There's actually who knows. Just raise your hand if you know. And I mean, there's the usual suspects. Okay, so that's good. That's a small subset. It's less than half of the participants. And I guess that means that even a smaller group of you would maybe describe yourself as working in this area or having worked in this area. That kind of gives me a feeling for what I can talk about. I should also say that, so data-centric engineering, of course, is also a new term and one that is maybe filled for different people with different content. So apologies in advance if I'm using lingo that maybe is only addressing a subset of the community. I would describe myself as coming from a domain called machine learning within computer science. That's where we publish our papers typically. But of course, that area is strongly related to data science, to computational statistics, and maybe also to some way of filling the term data-centric engineering. So I'm going to use lingo from machine learning, but I think it applies to many other different settings. When you ask people in the public, in the media, what machine learning is about, or data science, or computational statistics, then you might read that it's about building computer programs that refine a model using data. So there's your data centrism. But both of these things, model and data, are actually external, right? They arrive in the computer from the outside world. The model arrives provided by a human programmer or a user, and the data arrives from the physical world on the hard drive somehow. What actually happens on the computer is, of course, a computation. And in contrast to classic AI, rule-based AI, where the computations were typically discrete and closed form, in contemporary machine learning, the computations are numerical computations. And by that, I mean the computation of quantities that have no closed form expression and which cannot be computed to infinite precision in finite time. They are integration problems for any kind of probabilistic inference to compute conditional distributions and marginal distributions and evidences. They are optimization problems to fit and estimate frequentist properties or quantities or estimators, or to minimize empirical risks. They are the solution of differential equations, so simulation tasks to predict what will happen in the future for in machine learning tasks like reinforcement learning, but also in scientific applications, in econometric applications to predict what might happen next. And of course, linear algebra, because linear algebra is the base case of everything for Gaussian integrals, for quadratic optimization problems, least squares problems, and for the solution of linear differential equations. Now, of course, there are numerical algorithms for all of these tasks, and they have been invented 30, 50, 100 years ago, depending on which of these areas you think about. And they arrive in our relatively young community as pre-packaged pieces of software, as software libraries that have been optimized over time. That's good because it means that people can save a lot of time by using these tools. But, and that's going to be a main theme of this talk, I would argue that these methods that have been around and have been originally invented for different tasks are not perfectly suited for some of the key challenges and aspects that arise in contemporary data science, machine learning, computational statistics. And here are a few of these challenges. So as a placeholder for all of machine learning and data science, you could think of an empirical risk minimization problem. So let's think of, just so that we have something concrete to think about, a deep neural network, for example, that is described by a loss function that happens to be a sum over many different terms, where every term in the sum depends on one datum, one individual data point, and all of the parameters of the neural net, the weights of the neural network. Now, there are several different challenges inherent here if you want to optimize such a function with respect to theta. One of them is that theta tends to be very large. So the size of the parameter space is by practitioners often chosen such that it exactly is equal to the memory size. It's just that one gradient of the neural net fits exactly into the cache of the GPU, for example. That means that tools that build statistics over these quantities are challenging to realize. For example, quasi-Newton methods, which keep around a limited memory of recent gradients, might not be applicable because you can't even store several gradients. But that's not maybe the main challenge. The main challenge, in my opinion, is that the data set is large as well. So everyone here surely has heard about big data or is really sick of that term. So for me, big data means that n here is a large number, so large that when an optimizer asks for a gradient of this function, you cannot go through the whole sum. Instead, people do what's called mini-batching. They uniformly sample from, or IID sample from the whole data set, a smaller subset of the data, a batch, and compute an estimator, a random number for this quantity. So that random number, because it's IID and it's a sum of IID random numbers, is basically approximately Gaussian distributed with some caveats, with a variance that has something to do with the batch size. And what that means is that this problem is so stochastic that, so typical batch sizes in machine learning are, for M, are 1 or 64. These problems are so stochastic that you cannot think anymore in the way that classic numerical stability analysis works, that you think of the computer computing the quantity it's actually supposed to compute, and then actually getting a number back that has a small deviation, a small perturbation relative to the correct number. Instead, you really get a random variable returned by the computer. So computations in this kind of domain, in this age, are so stochastic that the stochasticity is actually the defining characteristic. It's not a small second order kind of correction, a small perturbation. It's the thing that you get out of the computation. It's an entire probability distribution. By the way, this, for example, means that you need at least two quantities to describe them, not just the computed estimator, here random number, but also its error bar around it. Thankfully, you can actually compute these quantities. And a third problem is that increasingly now these days, actually, the kind of computations, the kind of inference tasks we'd like to solve involve several different sources of information. And here I want to teaser one example problem that is actually very much contemporary. It's of like a very 2021 kind of nature. Here are, I mean, everyone is by now sick of these kind of plots, of these numbers. Here's a, well, you know these data sets. This is the COVID case counts in Germany, actually, over the last year. I deliberately stopped the data set here in like the middle of this year because I don't want you to think about me giving advice about COVID strategies here. So I deliberately kind of leave it a bit in the past. But here, this is a typical setting where we need to infer something, an unknown like future dynamic of a dynamical system, and we have two very different sources of information. On the one hand, we have empirical data, numbers that are available on the hard drive. And if you would run a black box standard statistical estimation tool or machine learning algorithm on this, like a kernel-rich regressor or a Gaussian process regressor or a deep neural net, if you imagine what it would do to the right to extrapolate where you actually want to have a prediction, then it's probably not going to work well, right? It will just extrapolate, I don't know, linearly or constant or return to zero depending on your model. It's not actually going to contain interesting information about the future. On the other hand, we have mechanistic knowledge. So we know that like pandemics follow some dynamical system that can be described through an ordinary differential equation in this case maybe, so an SIR model, type model. So there are groups of people that are either susceptible or infected or recovered or vaccinated or dead. And you move from one of these groups to another according to this differential equation. But we don't know this differential equation perfectly. There are parts of it we don't know. So for example, in the SIR models, there's this beta in here. That's the contact rate. It's how often people actually interact with each other. And you can't typically directly measure that. Clearly, that contact rate changes over time. If it wouldn't, if it were constant, then we would have seen early in 2020 an exponential increase until everyone was infected. That didn't happen. So what the underlying explanation for this is that people change how often they interact with each other because of lockdowns, because of psychological effects in the population. And here there's an entire function here, beta, which we don't know. So neither of these two sources of information on its own is sufficient to predict what will happen next. But together, maybe they inform us of what might happen. And we need numerical algorithms that can deal with both of these, like both of these sources of information at the same time. So they are able to work with what I might call a chained computation, several computational steps one after another, in addition to the other two challenges I just mentioned, stochasticity and high dimensionality. So we need new numerical algorithms. And of course, we could wait for applied mathematicians to realize that that's necessary. But what I'm trying to convince you of today is that if you've worked in the analysis of data as a statistician, as a computer scientist, as an engineer, then you actually have the right tools to think about the numerical algorithms you'd like to build. And that's because numerical algorithms are inference engines. They are learning machines. And numerical algorithm is a quantity that estimates, it's an algorithm that estimates an unknown quantity, like for example, the value of an integral, from evaluations of tractable quantities, like for example, values of the integrand or noisy values of the integrand at various points. And that means they are estimating a latent quantity from data. It's just that the data doesn't come from the hard drive, like we normally think, but it comes from the CPU or the GPU. But conceptually speaking, that doesn't really matter, right? Where the information comes from it's just an afterthought. So we can think about computation as an inference problem. That means we can think about computation as an inference problem in the probabilistic language as well, in the sense of Bayesian inference. And we can think about numerical algorithms that use this framework to describe what they do. They take probability measures as their input, refine them using the data they can compute with noise, using Bayes' theorem, and return as their output another probability distribution or measure or density that assigns a meaningful notion of uncertainty to the value of the unknown quantity, of the integral, for example. And we call these algorithms these days probabilistic numerical methods. Actually, we've been calling them probabilistic numerical methods, to point out something that Chris mentioned at the beginning, since at least 2012, so that's like 10 years that we've been, like some of us have been working on this. Also, some of you here on the call today. But this idea that you can think of computation as inference is actually way older. It was already pointed out by Henri Poincaré, like basically around the same time that Bayesian inference was formalized. He already thought about things this way, and then by many other people later on as well. I'm going to link to, or actually up here, you can find a link to the ProbNum webpage where you can find a list of historic literature on this kind of domain. But it has really picked up speed in the past few years because several people, some of them here in this call as well, have become interested in it and started working on it from very different directions, with sometimes a theoretical, sometimes an applied kind of bent. What I'd like to do now is to show you an example, one example domain, and focus on that also for the rest of the talk, and that's differential equations. That's not because there are no probabilistic numerical algorithms for the other domains. In fact, there are, and I'll show you a link to a package, software package that addresses some of them later on. But it's better to think about, one concrete problem, so let's think about differential equations. So for the purposes of just the next few minutes, I'll think about ordinary differential equations. So those are equations that describe the behavior of a curve. So x is an unknown curve that is indexed by a real number and has potentially multivariate real valued output. And we don't know that curve. Actually, in this plot, it's this black thing, but let's assume we don't know that thing. But we know that its derivative with respect to time, the scalar input, is related to is provided by implicitly by evaluations of a vector field f. So those are these arrows in the background. And maybe one thing we might know is that the curve starts at some point, and it's called an initial value problem, of course. So there are many algorithms to solve these kind of tasks, and actually those are maybe some of the oldest numerical algorithms ever. They're certainly like 100 years old or more in the case of Runge-Kutta methods. And what I'd like to tell you is that you can think of what these methods do, even the classic ones, as solving an inference task. So forget for a moment everything you know about how to solve ODEs, if you do, and let me tell you one way of thinking about how to do that. Imagine we know what the initial value is, actually. If we do that, then we know that the curve has to go through this little black point here on the left. And clearly that means we can evaluate this vector field at that point, and it provides us information. It gives an observation of the gradient of that curve at the initial value. We can use that to condition some prior, I'll tell you which prior in a moment, on that these observations. There's actually now two observations, the initial value and the gradient, and use the resulting posterior or conditional distribution to predict into the future what the solution of the ODE might be going forward. Then you can use that to build a node, an evaluation node of where we evaluate the vector field again to get another observation of the gradient of this curve. And then we can iteratively step forward through time to eventually get an estimate for the true solution of this ODE. That's this red curve with an associated posterior probability measure around it that we can draw samples from. So this is actually not, of course, how ODE solvers are classically phrased, but it provides an algorithm that has the exact same interface as a classic method. And so instead of calling a classic ODE solver, there is a corresponding method that you can call that you hand the same things to, a handle to the vector field, a region over which you want to integrate from the left and the right, and an initial value. And what it returns then is a different object to what a classic method would do. So classic methods would return this red line in the middle, and maybe an error bar at the end, like a tolerance scheme. And instead, this algorithm returns this full probability measure, or PDF actually, which actually, as it happens, a joint Gaussian distribution from which we can draw these samples. Now, as it turns out, there's a class of algorithms that we in my group and a few others have been studying for quite some years now that provide this functionality, and they provide it in such a way that they match the performance of the classic algorithms in the sense of computational cost and approximation quality. So that means the runtime cost of these methods is comparable, it's in the same complexity class, and the quality of the approximation, so the difference between the red and the black line, contracts as you increase the computational budget of this algorithm, as you decrease its step size towards the truth at a high polynomial rate. So for classic ODE solvers, the ones that are widely used, that rate is like 5, but there are also methods that have like 8, 9, 10, and so on, and we can basically get those rates as well. But there's a new additional quantity, which is this region of uncertainty around the estimate, and it turns out that, so this is a new kind of quantity, right? So it turns out that this region of uncertainty can also be shown to have good properties. It contracts towards the red line at a rate that can be thought of as a worst case bound, a relatively tight worst case bound for the difference between the red and the black line. So it's a meaningful error estimate. So how do these methods work? Actually, how do you actually implement them? Let me tell you, let's open up the black box a little bit and tell me how these methods are constructed. They are Kalman filters, or Bayesian filters and smoothers. So I hope that many of you here in the audience, if you have a background in sort of signal processing engineering, you've heard about these filters and smoothers before. They can be described as probabilistic inference algorithms that arise from a Markov chain structure in some latent state. So we model the solution, just like in a normal inference problem, like if you just want to do regression, you can learn a deterministic function by assigning a stochastic process as a prior. Here we do the same thing, it's just that both objects are differential equations. We assign a prior that is given by a tractable, linear, Gaussian, stochastic differential equation, and use that to infer the intractable, nonlinear solution of the deterministic ordinary differential equation. And for that, we describe a state space. So we define some multivariate variables x that have entries, such that the first entry, the 0th entry of this stacked vector of entries x, is supposed to be the solution of the ODE, and the higher order elements of this vector are supposed to be derivatives, higher order derivatives of this ODE. And then we can describe the behavior of this Markov chain with for example, a stochastic differential equation, so continuous time representation, or we can discretize the stochastic differential equation and describe it as a filter, or well, actually describe inference in this Markov chain as filtering. Inference from what? So what kind of data should we look at? Well, we want to convey the information that the derivative of this curve, the first entry in this vector, is related to the 0th entry in this vector through the ODE. So that the difference between the derivative and the vector field evaluated at the 0th entry is 0. And so that is provided by what's now called an information operator. That's due to work by Philipp Hennig and others. So a Dirac point measure, basically, that says these two things are equal to each other. Now notice that, of course, this likelihood here, it contains things we don't know. The first derivative and the 0th derivative. And one of them, the 0th derivative, goes through a nonlinear function. So to make the inference tractable, we have to build an approximate model for f. And we can do that through linearization using automatic differentiation. That's called the extended Kalman filter. And extended Kalman filters look like this. If you've seen Kalman filters before, then you will immediately recognize this kind of code. If you haven't, then you don't need to be able to parse this code. What I just want to highlight is that this is a for loop that steps forward in time. And at each iteration of the loop, there is a lot of simple local linear computations to be done. Everything here is just linear algebra. There is no nonlinear operation inside. So these algorithms can be realized in practice, and in fact, they have now been realized. So for quite a while, probabilistic numerics was a relatively academic field of study, I think, where people have mostly just pointed out these very interesting connections between algorithms. Now we have, thanks to the work of many people, myself actually pretty much excluded. I've just been helping to set up the structure for it. I haven't written the code. We've been able to build a software library. Actually, here is the website for this as well. I encourage you to have a look. It's very easy to install if you're operating in Python. Very, very simple to use. There are tutorials and introductory material on this website. A library that provides these algorithms, not just for differential equations, but also for integration and for linear algebra, and soon also for various other kind of applications. In particular also integration. So if you've ever worked in the development of numerical algorithms, then you know that once the theory is done, that you're far from having a workable algorithm. There's always a sort of painful step afterwards where you actually have to make sure that these algorithms work in practice. And this is the reason probably why many of us, and maybe you as well, tend to rely on established packaged pieces of software. What I'd like to convince you of in the next few minutes is that this piece of software here is actually approaching the quality of these pieces of software, these older ones that you might be used to using. So we've really spent, in particular, the PhD students who've worked on this have really spent some time making this code work well. Here's a few plots that are supposed to show this. Here's a initial value problem being solved. On the left, you see, the top left, you see the problem. It's a restricted three-body problem with an orbit of a space probe around a sun-Earth or moon-Earth system. And what you see here are various plots that compare the algorithms in the toolbox, in this ProbNum toolbox, to established solvers as implemented in the SciPy library. Here you see a comparison of the local error between a Runge-Kutta method and a corresponding probabilistic numerical algorithm. And you can see that they are pretty much the same. There are two different algorithms being compared here, one with order 5, one with order 8. And you can see that they're sort of performing equally well, roughly, to each other. The same goes for global final error at the end point of the integration. Here the algorithms are also good at adapting their performance to required tolerances. So they roughly reach the tolerance they've been designed to achieve they deviate from the actual value, but that's actually quite typical for these kind of algorithms. That goes for the classic ones as well. They achieve the convergence rate they're supposed to achieve. So as a function of the number of evaluations, the error drops with a certain rate. Depending on the implementation of the method, it's like up to a very high order, up to order 11, so high that basically you get a vertical line almost. So there's basically not much difference anymore, not much reason to increase the performance further. And by the way, I should say that these are plots from an upcoming paper by Nico Krämer, one of the people who've spent a lot of time implementing these algorithms in this Python toolbox. And finally, we're also getting close in runtime. So here is a runtime wall clock time comparison for the same kind of error estimate between the probabilistic algorithms, the one with the additional functionality, and the classic Python implementations of these algorithms. And you can see that there is still a gap. Depending on how you want to read this plot, it's between a factor of 10 and 100. I'll answer that question in a moment. And so there's still a gap, but actually I think that gap is now so small that it actually doesn't matter anymore. Then we also know where it comes from. It's from like advanced memory management in SciPy. But it turns out you can also implement these same algorithms. So another one of my PhD students, Nathanael Bosch, has ported the same library to Julia. Maybe some of you use and like the Julia language, which tends to be perform better because it's compiled code. And here you see a comparison between these algorithms as a function of their final time error and runtime on a Lotka Volterra simple test problem, and compared to various different other implementations. So here at the very top, so you can first of all, let's see that you can understand this plot. You kind of want to be in the bottom left corner, right? So you want to have fast computation and low error. And of course, as you decrease the error, the computation time goes up. And you see in gray at the top, MATLAB code, in green, Python code, standard implementation, so not ours, but like the standard, let's call them commercial off-the-shelf solvers. In blue, classic Fortran code from, I think, the 80s by Antara. Then here in dark red, various Julia implementations of different solvers. And you can see that they tend to be quite fast because Julia has a very active community to build super efficient ODE solvers. And in fat orange, this other stuff, by the way, yes, I think C code. And in fat orange, the probabilistic solvers in Julia. Now, still, there is a gap between the Julia implementations of the classic solvers and the Julia implementations of the Pdes of the ProbNum solvers. But if you're the kind of person who is currently content solving their ODEs in MATLAB or in Python, then you should be content with using probabilistic solvers now because they achieve basically the same computational cost. The gap between the probabilistic and the non-probabilistic solvers is smaller than the gap between programming languages. These algorithms are also now adaptive, so they adapt their step size and calibrate their uncertainty in the same step. These are plots from a paper by Nathanael Bosch and Philipp Hennig and myself that was published earlier this year. What you see here is basically a calibration plot. So for different ways of calibrating these methods, you see plotted against the numerical error, like the approximation error of the algorithm, a chi-square statistic. So that's the square error, square actual error, so the difference between the estimate and the true value squared, divided by the variance, so the estimate for the error, for the square error that the solver returns. If that kind of, given that this is a Gaussian model, this kind of quantity should be distributed like a chi-squared random variable. The green region is the 99% confidence interval. And as you can see, we sort of hit that interval quite frequently. It's not perfect, but again, this is a numerical computation that is achieved with also a bit of a trade-off for computational speed. And I think this is a relatively good kind of result, given that what we've seen in the past with these methods. I think we're now really at a relatively good point. So in this section of the talk, even though it was arguably maybe a bit dry, I wanted to really get across that we've spent the time, and when I say we, it's many people have spent the time now to make these algorithms work. If you've heard about probabilistic numerical algorithms before, and you thought they're maybe not quite right ready for the limelight yet, I think they are now, thanks to the work of many hardworking people who built this kind of code base. So, though, what would you use these algorithms for? So, when I started working in this area, I actually thought that people would be excited about, let me go back, plots like this and say, this is exactly what I want. I want quantified uncertainty, and that's like the killer functionality for these kind of algorithms. But I had to learn, and I understand this now in hindsight, that that's not really enough for people. Just being Bayesian in statistics is not enough to actually convince people that it's useful for anything. You have to show that you can actually do things you couldn't do with like the classic methods. Partly also because when people solve differential equations, because they're using a black box, they tend to just set the tolerance of that box so high that the output is so precise that you basically don't need an error estimate anymore. So let me go back to this problem that I mentioned at the beginning, and this COVID case counts, and highlight a functionality that classic solvers patently cannot provide that are really straightforward to do in probabilistic solvers. And that's the joint solution of, or joint inference on the path of an ODE and the underlying ODE. So if you are working in applied mathematics, you're surely aware of the terms inverse and forward problems. For me, as a sort of pedestrian way of phrasing what these problems are about, you could think of a forward problem as the task of, I give you the ODE, please tell me what the solution of this corresponding initial value problem is. So I know what the vector field is, what is the path, the trajectory of the dynamical system. While an inverse problem is the opposite thing, right? I've observed a trajectory, or maybe several trajectories of a dynamical system. I'd like to know what the underlying vector field is. So this clean separation between forward and inverse, I think, served applied mathematics well for several decades. But in these days, when we have these mixed data sets, where you observe trajectories and you have also uncertainty about the vector field, so finite uncertainty, right? You know something about the vector field, but not everything. But that thing you don't know might even be non-parametric. It might be an entire function you don't know. This separation is, I think, is reaching the end of its utility. Let me phrase it aggressively like that. So why? Well, because people still think about these ODE solvers as a black box, as something that just does its task. Actually, let me show you an example so that you know that I'm just not making this up. Here is, or let me see if I can move around. Here's an example from a probabilistic programming toolbox called NumPyro. I don't want to diss that community, by the way, at all. So this is really cool code. This is a very advanced, in fact, I want to use it as an example of how extremely advanced code still does this. This is maybe one of the most up-to-date, efficient probabilistic programming packages. And here is an example from their own tutorial on how to use their toolbox for inference in a particular dynamical system. Here it's a Lotka-Volterra type predator-prey kind of problem. And so you have trajectories, so you see these dots, right? And you'd like to know what the parameters of this predator-prey system are. And here's the code for this. You don't have to read the whole thing. What's happening here is that someone defines a differential equation. That differential equation contains parameters. In this case, they're called theta. They're like the contact rate in this COVID model I mentioned before. And then the actual business end of the model, where everything happens, just calls an ODE solver, right? And just provides the theta, the parameter, to it, and does it forward. And then it has to do that call, this call through the model, many thousand times, over and over and over again. So you start with one value for theta, then you predict forward, you get a solution that doesn't look like the data. You try to compute a gradient. Thankfully, these days, you can compute these gradients very efficiently using advanced automatic differentiation libraries like JAX. And they contain ODE solvers. Here is JAX's ODE solver. What does that solver actually do? Well, it calls a 50-year-old ODE solver called the Dominant-Prince pair. So it's a Runge-Kutta method of order 5. And it basically just re-implements that method. You can look at that code yourself. So what that means is that we have here an outer loop here, repeatedly solving an ODE over and over and over, and then an inner loop, which involves the actual ODE solve. And that is wasteful. Anyone who's written computer code before knows that if you have nested loops, those are sources of inefficiency. And the reason we do it that way is not that the solver cannot deal with it. In fact, I'm going to show you in a moment that it can. because these solvers are filters themselves, they already are well, actually, I'm going to show you the result. Maybe like this. So let's go back to this data set. So we have two different sources of information. There's an ODE, which contains parts we don't know. And then there is a trajectory, which we can measure, but that trajectory is not sufficient to extrapolate into the future. And we can think of both of these as sources of information about the exact same quantity, the curve, let's call it X, that subsumes this entire set of states across time. It's just that sometimes we observe values of I, the number of affected people, and sometimes we observe the fact that this equation holds. And within a Kalman filter, both of these are just different observation models. So I started half an hour ago telling you that you can think of ODE solvers as running a filter on a Markov chain where you locally get observations of the fact that the ODE holds. But there's no reason you couldn't have intermediate steps where you also observe what the trajectory is. And there's no need to have one inner loop that deals with Z and then one outer loop that deals with Y. You could have one joint loop that does the same thing in one forward pass. And you can use the information collected from Y to inform yourself or the algorithm about quantities that actually show up in the ODE that you don't know, like the contact rate or like the parameters of this Lotka-Volterra model. So to show you how this works, I'm going to show you output and data from a paper that will be in New RIPS this year, written by the aforementioned Nico Krämer and Jonathan Schmidt, a master student in my group. And what you see here is, again, at the top, this in black, this data that I've mentioned before. It's case counts over time for COVID in Germany. And so we would like to infer the solution of the ODE that drives these numbers, these infected numbers. How does it continue to the right here? And in the second plot from the top, you see an estimate for this contact rate beta. And it's actually a Gaussian process. It's a transformed Gaussian process, a squished Gaussian process. You can see that at the beginning, we just have a prior that's very, very vague. It's not very uninformative so far. And the bottom plot, by the way, shows vaccination rates, because back then we were too bold and overconfident and thought that vaccinations would rise towards 100% by July, and then things would get really interesting. Of course, they didn't, and now we're in that mess that we're all in. So what I'm going to show you is how this solver proceeds to condition on both the ODE and the observed trajectories at individual steps in time. So the plot is maybe a little bit confusing in the sense that we always show what the solver would predict if it would only solve the ODE forward. So you get this initially really sort of crazy estimate for that everyone wanted to avoid back then. And now imagine that it steps forward through time in a single forward pass. So one unique single ODE solve. And at every point in between the data points, it just conditions on this information operator, on the fact that the ODE holds. And then whenever there's a data point in the trajectory, it just conditions on that observation. And so then what then happens is that as we go forward in time, initially we learn very little about the contact rate because there's very little data. There's almost no one infected. If there's no one infected, you can't observe that these people infect other people. And so we're very uncertain about what the contact rate is. But as soon as the numbers start rising, we see that the curve flattens. And the only explanation for that is that the contact rate must have been low and it must have descended to explain this. This was the first lockdown in Germany. Then over the summer, case counts were again very low, summer last year, 2020. And when that happens, again, we have almost no probes in the population. So we learn almost nothing about the contact rate. And then as the second wave hits in towards like the end of 2020, early 2021, we again learn a lot about how the contact rate evolves. And this is, of course, as an effect of lockdown measures that were in place back then. And yeah, okay, then we can run the solver forward all the way to the end. And it will then, at the end, output a prediction for the further path of this ODE that keeps track of both the dynamics described by the ODE, but also the uncertainty arising from the fact that certain parts of that ODE are not known going forward in time. And of course, we can also run a filter backward, a smoother backward, and draw samples from this distribution. Then you get, like in some sense, a approximate full posterior over the behavior of this dynamical system, including the unknown variables on the ODE and unknown future behavior of the dynamical system. And all of this happens in a single forward pass. So if you would implement this kind of inference problem, and actually Jonathan Schmidt did, in one of these probabilistic programming packages that I mentioned before, this kind of inference would take something like a day or two. And if you do it with this probabilistic ODE solver, you can run it on a laptop in a few minutes, 1 or 2 or 3 minutes. Why? Because you save one outer loop. Not because Bayesian inference is more expensive than frequentist inference, or point estimation is somehow easier or harder than Bayesian inference, but because by treating computational data, computational information, and empirical data as the same thing, you can condition on both of these quantities at the same time in a single for loop. And that's really, for me, the value, like one key value out of several others of these kind of algorithms, that they allow this kind of functionality. Just to drive home that point further, you don't necessarily just have to have information about the ODE itself. Maybe you have additional further information. Maybe you might know, for example, that you have a system that satisfies some laws, some conservation laws of physics, that it has some energy function, that some Hamiltonian that is conserved. So here at the top, you see at the left in black a Hainon-Hyles dynamical system that conserves some energy. It has a Hamiltonian. And so this is the true solution here, computed to very high precision numerically. In green, you see the output of an actually probabilistic ODE solver, the point estimate, if you do not condition on the fact that it conserves energy. But you can, of course, provide an additional information operator. Actually, it's down here at the end, that conveys information to the system that there is this function, this nonlinear function called the Hamiltonian that is conserved. And then you get this output here on the right. And this is actually deliberately computed with slightly lower precision so that you see that it's not the exact same as the black curve, but you can see that these curves look much more like they conserve energy. Now, of course, there are classic algorithms that do this, they solve this particular challenge as well. There are geometric integrators, there are symplectic solvers, and so on. But the key value of the probabilistic viewpoint is that all of these different sources of information, the ODE, the conserved quantities, and maybe observations of trajectories, can be combined in the same language. You don't have to have one special solver for every different task, but you can have one framework that does all of them and can do all of them simultaneously. There's various other kinds of information you can also use, like, for example, the fact that an ordinary differential equation might be known to be second order or higher order. You may think that that's not informative, but it turns out it is actually a useful information, and various other kinds of algebraic information. So with that, I'm pretty much at the end. Let me summarize a little bit. The main point I wanted to get across is, and by the way, maybe what I just did is an answer to the question in the chat. So like, there are various other classes of ODE solvers. I would say that these algorithms are competitive with the standard off-the-shelf solvers like Runge-Kutta 4.5. And yeah, I'm not going to make an argument against any other solver that I might not even know much about. So the main message I wanted to get across is that you can think of computation as inference. So if you're someone who knows the language of statistics and inference, then you can think about, you have a license to think about computation as well. That doesn't mean you get to ignore all the work that numerical analysts have done in the past, but it means that you can combine their knowledge with yours. And we can think of computation as the collection of data. It's just that the data gets collected by the computer itself, if you like, in silico. The way to phrase this mathematically, in my opinion, is provided by probabilistic numerical algorithms, which quantify sources of uncertainty and information arising from any source in this process, from the data, from the computation, from algebraic knowledge, mechanistic knowledge. I showed you an example, an extended example of this in the form of probabilistic ODE solvers, which are algorithms that in some sense match the structure and the performance of classic algorithms in the sense of computational cost and convergence rate. But add additional functionality like calibrated adaptive uncertainty, but also the ability to deal with a richer set of information, like conservation laws, like observations of trajectories. And in doing that, in some sense, they blur the boundary between forward and inverse problems, between geometric integration and normal solution of initial value problems, if you like. In this sense, I'm convinced that probabilistic numerical algorithms provide genuinely new, valuable functionality, and that the only reason people haven't maybe started using it yet is that there wasn't good code around to try it out, and I hope that we're now really addressing this with the release of the Probabilistic Numerics library. If you'd like to know more about this kind of work, you can check out the work of my research group on this webpage, and because this webinar is sponsored and run by Cambridge University Press, I might be excused for pointing out that there is a book coming out on this topic by Cambridge University Press called Probabilistic Numerics, Computation as Machine Learning, written by myself and Hans Kersting and Mike Osborne. It's currently with the copy editor, so we are hopeful that it actually will come out in early 2022. And yeah, I think that's it. Thank you very much for your attention, and I would be very happy if there were questions in the audience.
Great, thank you very much for that. Would you like to start by answering the questions in the chat?
Yes, so there is a question. Okay, so I'll just read it out. How do these EKF numerical solvers compare to path integral solutions? So I'll have to admit that I don't know what exactly you mean by path integral solutions. So if you are thinking of what is sometimes in the computational physics community called a path integral solver, then those are essentially Gaussian process algorithms. So they are very similar in the conceptual nature. I would say that, to my knowledge, these implementations, that these specific filters with their adaptive functionality, are maybe a more practically minded realization of these algorithms that scale to larger problems. If you're thinking of a more elaborate path integral solutions in the sense that, so then I would have to say I just don't know. So there are also people in, for example, reinforcement learning that think of path integrals that have non-Gaussian solutions, and then those are pretty much abstract analytical and non-analytical objects. So I'm not sure how they relate to numerical algorithms. So someone asks, is it possible to extend to PDEs? Yes, it is. So it's possible in various different ways. Actually, let me show you a slide from my backup. Here we go. This is a recent paper that you can find on the archive at the moment. It's currently under review by the aforementioned Nico Kremer and Nathanael Bosch and Jonathan Schmidt, the ODE PhD students in my group, where they've extended this solver such that it can deal with a very large state space. So here you see what is arguably a time-variant PDE. It's a high-dimensional Lotka-Volterra system where over time, you see at the top is the point estimate, and at the bottom is the uncertainty estimate. You can see the development of this system, and it's sort of typical for these types of models that they build these kind of constrained regions of where like the predator and the prey like eat each other and then build these kind of interesting structures. And this paper is about how to scale up to these high-dimensional systems. There's a separate paper which they don't have the citation for here in these slides, on how to solve time-varying PDEs with this method. This is called the probabilistic method of lines, if you want to Google for that. So for time-varying PDEs, you can actually basically borrow the functionality of the Kalman filter and model the behavior of the PDE in the transition probability of the filter. An advantage of that is that it provides a joint scale for the discretization uncertainty of in both directions, right? Both in time and in space. And that allows trading off the precision, the computational resources invested in refining the grid of the PDE or refining the step size of the ODE solver. If you're thinking of non-time varying PDEs, so the sort of like the larger class of PDEs that probably more people are thinking of, then I would say yes as well. And there is in fact various work by various people also in this call and also from my own group in this direction. And here the story is a bit more difficult to tell in a few seconds because it basically comes down to very complicated questions of probabilistic linear algebra. Because PDE solvers are often to some degree like recasting the solution of the PDE into a large scale linear algebra problem. But yes, there is work on this.
on the extended Kalman filter question, I was wondering, so there are alternatives to the extended Kalman filter, such as the uncentered Kalman filter. Is it possible to use these alternatives, or you?
Yes.
Yeah,
so
okay.
there is sometimes I wish I should probably make a slide of like old papers. So there is a paper by Hans Kersting from 2018 on how to use the uncentered Kalman filter for this kind of purpose. There's also work by Philipp Hennig on using particle filters for this purpose. And of course, there are also, I should say, probabilistic numerical solvers that are totally non-parametric. So, for example, Tim Sullivan, who at least wasn't at the call here earlier today, he's still here, and various others have worked on sampling-based ODE solvers that return a set of samples. So they're basically like Monte Carlo methods. These algorithms have the advantage that they are, in principle, totally non-parametric. So they really build non-Gaussian posteriors. They also arguably have the disadvantage that every single one of these solvers is completely an independent ODE solve. So there's now a spectrum of these probabilistic numerical solvers that run from, I would say, very practically minded, so where uncertainty is kind of maybe not the primary thing to do, but we are kind of trying to achieve the performance of classic methods and then add functionality to them, all the way to really focused on uncertainty quantification, where the goal is really to figure out what the error, like the non-parametric error of the solver is, and get a calibrated posterior. It turns out that these methods are also really useful. I've recently been involved in a collaboration with neuroscientists where it turns out that using these sampling-based solvers can be used to provide scientists with a good intuition for how precise their numerical algorithms actually are. And sometimes it can turn out that scientific statements that are derived from the simulation with these probabilistic these non-probabilistic solvers can actually be misleading because they're very subtle, like numerical errors that kind of add up over time if you simulate sufficiently complicated and highly nonlinear systems like neural networks, for example, that spike, right? Okay, so another question is scalability to high-dimensional problems an issue? So I would like to, again, refer to this paper. So if you want to open up archive paper 2110.11812, you'll get it like really up-to-date work on how to scale up these filters. And here the basic idea is to introduce factorization assumptions. So if you have a high-dimensional state space, so if your ODE contains very, very many states, in this case millions of dimensions, then you have to assume that the individual states are independent of each other and their derivatives are not independent of each other. So you get like a block diagonal structure in your covariance matrix, and then everything can be run at very high speed. You might think, if you're a statistician or someone who deals with probabilistic models, you might think that imposing factorization is a dangerous thing to do, and I would agree, coming from this community. But actually, it turns out that the numerical algorithms that are used for this purposes classically, they make a very analogous kind of assumption. So the quantities, the sufficient statistics they track are quite comparable. And in fact, I mean, as you can see in this picture, you still get an interesting structured posterior out. So you still get a plot like this, right, where you can see that the numerical error of the solver is higher in the sort of the boundary regions of these domains, right? And you can see that over time there's like an early phase of high uncertainty, and then the uncertainty actually kind of collapses towards the end because the system goes into a stable state. So there's still interesting functionality to get from that.
So we're almost at the end of our time. So would anybody like to ask one final question? If you can type really quickly, ask the question.
I think you might even be able to unmute. No, you can't. I think you can't unmute yourself. Yeah, but you can type.
Okay, there's one final question from Raoul.
How does the computational time compare to conventional approaches? Okay, so I'll go back to this. I think this. I've mentioned it, and I want to say it again because I think this is really important. So at the moment, the current implementation of so when we started work on this, so the first time I dabbled in these kind of solvers, we were super unprecise about them. We implemented them as generic Gaussian process regression algorithms that are cubic in the number of in cost and the number of evaluations, and they were not comparable at all. Like they were 8 orders of magnitude away from the kind of performance that something like SciPy provides. Here in this plot, you can see a runtime comparison as a function of the prediction error between a classic implementation of Runge-Kutta dominant prince 4.5 in SciPy and 8th order Runge-Kutta method in SciPy. These are these thin lines in the background. And the current state of the software library. Those are these solid lines here. And so this is log time distance. You can see that the convergence rate is the same. Right? So these lines are parallel to each other, but they are off by, well, you know, if you eyeball it, something like maybe a factor of 10, maybe if we are cautious, a factor of 100. So that sounds like a lot, right? I can encourage you to do the tutorials for this software library online, because if you just run the code yourself, you'll notice that for the typical small ODEs you might be interested in, you won't notice the difference because it's so fast that it just runs anyway. But again, if you're worried about that gap, so the way to close that gap is to go really deep into the code base and do better memory management. So it's an annoying fact that good code takes more time even to get right. But we are now in a region where this is actually really, like, we're really close to like competitive solutions. So here's this other plot that I mentioned before of a comparison of the probabilistic solvers here in orange when implemented in Julia. So this is the package probnum.diffec.jl by Nathaniel Bosch, compared to, on the same problem, various other solvers from MATLAB at the top in gray, all the way to very high performance, super optimized Julia code at the bottom. So we're in the range of other solutions in other software libraries. So if you are not the kind of person who currently has switched to Julia because they really need that final piece of performance, then and you're currently happy to use, you know, a MATLAB solver or a Python solver, or even like Fortran solvers by like that have been around for quite some time, like Dopri5.f, then you can basically use these methods as well. And there's not really a reason to worry about computational cost anymore. And only if you really need to, if you're like the Met Office and you have to squeeze out the last factor of 10, then okay, maybe then you really have to think about getting this code to run faster. And if you are that kind of person who really worries about that, please get in touch with us. We would really like to optimize our code base further. But at that point, we really talk about, you know, very advanced code base optimization that also limits the kind of functionality then a bit, right? Because it kind of bakes in and crystallizes things. Okay, thanks a lot though for asking this question. I really want to get this across because I know that many people see this kind of work and think, yeah, maybe in 10 years time. I think the time is now to do that. And the reason for it is that it really provides this additional functionality. If you're still using a classic ODE solver, that's like using legacy code in an IT setting, right? And using these algorithms where the mechanistic and empirical knowledge really go together is, in my opinion, data-centric engineering.
Perfect place to stop. Thank you very much, Philip. So we're now at the hour, so we'll bring the meeting to a close. Thank you, Philip, for the wonderful webinar today, and thank you for everyone for coming along. This is also the last webinar for 2021, so there'll be some more next year starting 2022. So on behalf of everybody at Data-Centric Engineering, thank you for joining us for these webinars for the past few months, and hopefully see you all again next year in 2022. So, bye.
Goodbye.